Just a smidgen slow, and what I want to very briefly talk about is the fact that every classifier we've talked about, well, no, that's not true. Logistic regression and support vector machines both are inherently formulated as binary decision makers. It's a bird, it's not a bird. This patient is healthy, this patient has cancer. And many real-world problems are not binary, they're multi-class problems. I'm trying to classify if this student is going to be accelerated learning, normal, or if they need remedial attention. I'm trying to decide if this is a cat or a dog or a guinea pig or a mouse, right? Multi-class situations can be taken care of with binary classifiers. There are two extremely generic schemes that you can use to extend any binary classification, any positive class, negative class, into a multi-class situation. So, broadly speaking, we have one versus one and one versus rest strategies. Both of them will take several binary classifiers and turn them into a multi-class situation. Okay, 1v1 takes, in this case, a three-class situation. Okay, so we've got red, green, and blue, right? Those are our three classes. And it takes every pair that's possible to decide in there. Okay? So we have a blue versus green classifier, we got a blue versus red classifier, and we've got a green versus red. So the generic idea is if you have k classes, you need k times k minus 1 divided by 2 classifiers. So you need a lot of classifiers, potentially, right? Like when k gets big, that number gets big. It's roughly k squared. Okay? So if you have a lot of classes, this 1v1 situation requires a lot of trainings. So that's a potential problem. Okay, so now the way you know is this guy's going to say it's green, and this guy's going to say it's blue, right? And I don't know what this one says, but if we have multiple positive votes, how do we know who the winner is? Well, the answer is that we need to have a confidence score as well. So logistic regression gives us that confidence score, right? Logistic regression has a probability of correct. Okay? So 1v1 uses the class with the highest confidence score. Right? This one says green, this one says blue, this one says blue, but who has the highest confidence score in all of those? That's the one we go with. Okay? 1v rest is a different setup. In this case, we have blue versus everything else, and we have green versus everything else, and we have red versus everything else. Actually, you know what? These are actually 100% backwards, aren't they? This is my bad. I apologize, because that is exactly wrong. Because this guy only has k classifiers, and this is the one where we use the confidence score, right? Because every one of these is going to be negative class or positive class, and maybe we both vote green and we both vote blue. That's the one where you've got to use the confidence score to break the tie. 1v1, we have enough classifiers that we can go with the majority vote, right? So if both of these vote blue, then it's got to be blue. Okay? But if there's a tiebreaker, it's tiebreaker with the confidence score. This one requires a confidence score in the very beginning. Okay. I'm very sorry about that. I'm going to amend my slides and fix that and put it back out there. But it's 1vrest because it has a smaller number of classifiers that has to use confidence score immediately when there's more than one of these that votes positive class. Right? A negative class vote in a 1vrest scheme tells you nothing. It's a positive class vote that tells you what class it might be. And if more than one of these positive classes shows up, right, if it's both green and blue, then we pick the one with the highest confidence score as the tiebreaker. In this case, this is where we're going to get the possibility that we'll get multiple votes for blue. And so the multiple votes for blue, this is the one where you can just go with a majority scheme. If we vote blue, blue, green, then we just go with blue. And if for some reason we have a tie in terms of the numbers of votes for a particular class, that's when we go confidence score at the end. So that's how I knew that my slide was backwards. Does this make sense-ish? Because let me tell you, obviously in scikit-learn land, you will never have to implement this. It'll be implemented for you. You're not the one implementing the majority vote scheme, but it's good to understand what's going on under the hood. How can a binary classifier handle multi-class outputs? Now, there are also things that are inherently multi-class, right? So like a k-nearest neighbors, inherently multi-class. How many kinds of classes are in your training data? That's how many classes it can handle, right? It's not limited to binariness. But logistic regression and support vector machines and anything else that's just some sort of linear algebra, what side of the decision boundary are you on, that's inherently binary, and we've got to combine them. So scikit implements a bunch of ways, including the two that we just talked about, to do multi-class classification with any binary classifier. If you built your own binary system, you could inherit scikit-learn's 1vrest classifier into that class that you built, and it could handle this situation for you. Okay, need to make a small distinction between multi-class and multi-output. Sometimes life is not all one thing or the other. So ImageNet classification, I showed you it on Papers with Code. It has a hierarchical label system. So what does that mean? It means that a given image is both an image of a natural scene, it's an image with an animal in it, it's an image with a cat in it. So there's 3 separate labels, at least, for this one image of a cat, right? It's a cat, it's an animal, it's a natural scene. Whereas, in contrast, the picture of the ships in San Diego Harbor is a natural scene, it's transportation, and it's, ocean, and it's ships. So these are all different labels, right, that can be applied, and the labels are no longer mutually exclusive. When you're in that kind of classification hierarchy, that's when you're in multi-label land, okay? Where you can train it on a lot of different labels simultaneously. Some of those labels are mutually exclusive, some of them are not. And then, completely separate is that you can have multiple outputs on regression. We've always talked about regression as a single y value. No reason to limit yourself. You can do multiple regression where there's multiple y values that you're outputting for every single data point. So scikit implements all this stuff. There is, of course, a demo notebook that you can take a look at that's in the repo. That'll show you how to do some of these things, as well as the docs. Okay. It's kind of an aside. In my memory, we don't even have any assignments on this stuff, but I want you to understand how it works for your own good. If we do have assignments on that, you should probably let me know. I guess sometimes my TAs do things and I don't know what they're doing. Okay, but today, I should ask again, questions on the idea of different kinds of multi-class, multi-label situations. Yeah?
The only part of it that was kind of confusing me was the multi-output regression.
Mm-hmm.
When you say you're outputting multiple Ys for every data point,
Yep.
are you talking about doing different forms of regression on one data point?
Not usually, no. Usually, like, if you're saying that your Y is, like, you're trying to, for a given company, you're trying to simultaneously predict their gross and their number of employees or whatever, right, for every company. So that's a multiple regression situation. You're trying to simultaneously predict two numbers, but your math that you're using for one of them is the same as the math for the other. They're taking the same inputs. If it's a polynomial regression, they've got the same order, right?
So you're using the same data to answer two different questions.
Yep, simultaneously with one set of linear algebra. They are independent of each other. It's no different than fitting two separate regressions when you do that. Okay. SVM. So this was the cutting edge of machine learning when I was in grad school. It's not disappeared by any means, but I would say that definitely deep neural networks have become much more cutting edge than this stuff. Interestingly, you will find some neural network output layers do essentially implement support vector regression. Okay. So just a quick reminder, there's a mid-course survey. When I looked yesterday, there were only 55 respondents. I would like as much of the class as I can get. So it's on CampusWire as well as the slides. So the basic idea of support vector regression is I could draw an infinite number of decision boundaries in here, right? Who do we like best there, and why? Because none of the points are touching it, right? So can you extend that they're not touching it intuition into the land of statistics?
Your margin is wider on both sides for the points. How about higher, like what you talked about in the previous, like the gutter?
Yep.
Having a wider gutter, like a more efficient gutter.
Okay, so the deal is this, right? That blue line, that gives you more wiggle room if the next data point coming in has some pretty extreme noise on it, right? What if we get a positive class point that's just like it's way down here for some reason, right? So if we get a very low positive class data point, that black line or that purple line could be a bad choice. Even though all three of those decision boundaries are perfect with the training data, our intuition says that the blue one is going to be the least sensitive to more noisy examples, right? This is what a support vector machine does with a little bit of extra math. It's looking for the biggest distance between positive class and negative class that it can get, okay? We're going to draw in some margins, right? And so again, like the animation here is that, hey, if I get a negative class data point that looks like that, or a positive class data point that looks like this, I want to be robust against them. Okay, so the thing that we are going to try to do when we have separable data, so we're going to start with data where we can draw a perfect line where we have 0 training set error, because this helps us build our intuition. Obviously, we can then generalize the math to situations where the data points are not perfectly separable, where positive and negative class overlap, okay? We can generalize the math, but let's start with perfect separation, because it helps us build our understanding. So the way a support vector machine works is that it takes a look at where are the positive class and the negative class the closest together. Okay? I need to find a decision boundary which is smack dab in the middle, which has equal spacing to positive class and negative class, where I pick the slope and the intercept of this decision boundary such that I maximize this margin, this gutter, in the size of my street in between the 2 blocks is the biggest I can make it so that I can reject very noisy data points, okay, and still accurately classify them. Okay, so that's the math. The math is, hey, how can I make this margin as big as possible? Now, here's the details, and I went through this in much more time in the pre-video. So when you look at what we're doing, we're defining this thing called the positive hyperplane and the negative hyperplane. By definition, we're constructing these things, right? Here's our decision boundary. We're used to this. It's wx plus b equals 0. That is our decision boundary. We've seen this a million times. We're constructing the positive hyperplane as wx plus b equals 1. And we're constructing the negative hyperplane as wx plus b equals negative 1. That is, these lines are vertically 1 unit distance away from the decision boundary up and down. 1 unit of what? Anybody remember? 1 unit of what? Yeah? The inverse of the magnitude of the weight vector. This real distance in here, if you want to measure it in centimeters or whatever, it's 1 over the magnitude of the weight vector. And in the pre-video, we go through why that's true, okay? What in linear algebra land makes that true? But for right now, just accept for me that the size of the margin is 2 over the magnitude of the weight vector. All right? So our job is to maximize the size of the margin, which means what with respect to the weights? Somebody who's not him. Come on. Minimize the magnitude of the weights. Wait, what is weight minimization? What do we call that? Regularization. Oh my God, the very formulation of support vector machine for finding the right answer is simultaneously regularizing. This is a classifier whose loss function is inherently regularizing as we do it. So finding the best answers that give us the weight vector that gives us the biggest margin is also the most regularized that we can make it. This is why support vector machines were cutting edge when I was in grad school, because they were simultaneously finding the answer and regularizing, right? They're good generalizers for a variety of reasons. We're going to look at the other reason here at the end of this lecture if I'm fast enough. So, your intuition is this. When we have a tiny, tiny margin, we must have a giant weight vector. And when we have a giant margin, we must have a small weight vector and magnitude. Okay? Keep that picture in mind. Okay. But in general, support vector machines are just another linear model. So they have a function. That's the forward prediction. What class do I belong to? I don't know. Solve wx plus b, see what the sign is. That tells you what class you belong to. Just like logistic regression, they look identical, right? Can be in any kind of vector space, doesn't matter. The linear algebra is all the same. So their forward prediction time, test time, how we make predictions, looks identical to every other linear model. Okay? And we're trying to find the W and B that make the best prediction. All right. So that leaves us open to the question of how do we do their training? Right? That's the thing we haven't talked about. Prediction time, they're just a linear model. At training time, what we're trying to do is we're trying to squish the weight vector. We're trying to regularize. But, we could just do this. We could just say, oh, I'm going to make a W vector. I don't care what point direction it's pointing. I'm just going to make a tiny, tiny little weight vector that's going to have margins like this. And obviously, it's going to misclassify like hell, right? If I just try to squish the weight vector, I'll just squish it without caring about getting the right answer. So simultaneously with squishing the weight vector, we have to also try to minimize misclassifications. So that's this term. How does this term work? This is the so-called hinge loss. And the way you want to think of it is this. This stuff in here, wx plus b, okay? I put that in here. That's the v. V goes in there, okay? So 1 minus y sub I wx plus b, that goes in there. That's the hinge loss. This is the shape of my loss function. Okay, let's work through it. Y sub I is that trick we learned with logistic regression. When it's a positive class instance, this is a +1. When it's a negative class instance, this is a -1. And by having that y sub I out front, that means that this becomes the proper sign for talking about things being positive class or negative class. Either one, I can combine them into a single operation. Okay? When this is positive class, this whole thing is going to be some number that's positive. Well, if I'm on the correct side of the decision boundary, right? If I'm a positive class instance and I'm correctly classified, then wx plus b is going to be a positive number. So positive times positive is a positive number over here, right? And if I'm a negative class instance, correctly classified, then it's going to be a negative number times a negative number, and the overall result's going to be a positive number. So anytime I am on the correct side of the decision boundary, I am in a positive number. I'm over here on the graph. Anytime I'm on the wrong side of the decision boundary, I'm on a negative number. I'm over here on the graph. Okay? Now, let's look at more detail. What's this 1 here? Why does my loss stay at 0 anytime my number is greater than 1, and it becomes non-zero anytime I have a value less than 1? Well, that 1 represents the hyperplane that's either the positive hyperplane if we're talking about positive class, or it's the negative hyperplane if we're talking about the negative class. So what we're trying to do is we're trying to keep this gutter completely free of data points. if I have a data point which is positive class, it is on the correct side of the decision boundary, right? I classified it right. I predicted this as positive class, but it's in the gutter. It's underneath the positive hyperplane. Well, that is a number which is over 0, but less than 1. So I get some small amount of loss. Not a lot of loss, just a little bit of loss, because I let this data point fall inside the gutter. Okay? If I have a negative class instance, this negative class instance is completely on the wrong side of the decision boundary, right? It's misclassified. So that negative class instance is going to be over here. It's going to be on the wrong side of the decision boundary. It's going to have a much higher loss than the positive class instance that we did correctly classify, but it was in the gutter. Okay? So this is the hinge loss. It says, keep this gutter clean if possible, but really penalize much harsher any misclassification. Does this sound good? At least take some getting used to, I know, but like conceptually, hopefully you're running with it. Okay, so we got two terms here. Squish the weight vector to make the margin big. Keep the gutters clean and don't misclassify. We put them together as a team, and this is our loss function. We want to find the W's that minimize the regularization margin increasing term plus C times the hinge loss. Okay, this is the support vector machine loss function. Questions? No? Yeah? Ah, that is a constant. Good eye. Do you know how you know C under a different version? Guess what? It's the trade-off. It's a hyperparameter, right? How much, relatively speaking, do we care about squishing the weights and making the margin big versus how much, relatively speaking, do we care about keeping the gutters clean and minimizing misclassifications? So it literally is the same thing as lambda. It's just the inverse of that. You can write the equations either way. In support vector machine land, because the original paper on this used the C formulation, that's what we're going to use. But you can switch the formulation to a lambda formulation, obviously. Okay, so why this hinge loss? Well, we know some stuff about this, right? We know that if we just wanted to minimize misclassifications, we're up the creek because there's zero gradient everywhere. There's not an infinite gradient, right? So we can't do gradient descent on the misclassification loss, the 0,1 loss. But if you look at that hinge loss in blue overlaid, you can see that at least in some locations, it's very similar. It approximates the misclassification loss, right? But it has extra info, just like what we talked about. This thing, we have small penalties for being in the gutter, right? That's unique. That is totally different. Okay, so if we're going to do this, we've got this loss function. We've got two formulations of this, right? Here's a word formulation that says, I want to make my margin big subject to not screwing up my gutters and misclassifications. Or you can write it like this, right? Why do I even care about this formulation? Because they are equivalent. Well, the other part of support vector machines is a math trick that lets you make this computationally efficient, okay? So this is, okay, gradient descent, baby. I can write you the gradient descent. I can take this loss function. I can take the partial with respect to the weights. It's pretty easy. We know what this is. This is a W squared term, so when you partial it with the weights, it's a W term. You've seen this before. This thing, well, pretty easy, right? It's just a bipartite thing because you know what that loss function looked like. So when you're down here in the 0, well, guess what? Derivative is 0 because it's a horizontal slope, right? And when you're on this part that's going up, it's a constant slope minus yx. So, easy, right? Here's the bias term if you care about the bias term. But again, this can be computationally not the best. So here is an alternate way of solving this. This is the so-called dual form of support vector machines. This language is couched in the language of what's called constraint satisfaction problems. So again, I'm just lazy and I screenshot Wikipedia. You can go look at the Lagrange multiplier Wikipedia page on your own. But the idea is this. We have some function here in contours. That's f of x of y. Okay? But we have a second function that constrains the possible solutions to f of xy. That's g of xy here in the red. So we want to maximize f subject to the constraints of g. Okay? So lots of 19th century mathematicians, including Lagrange, put out a lot of effort in solving generic problems of this sort. And the so-called Lagrangian method is the way in which we can solve solutions like this in a very efficient way. Okay, the intuition of the Lagrange method is that we can replace our parameters with a linear combination of our data points. That's, okay, this is not a math class, so I can't prove to you the Lagrangian method, okay? I'm not sure I could prove it to myself, to be brutally honest. But this is what the Lagrangian method says. It says we can reparameterize our problem so that we completely replace our parameters w with a linear combination of our data points alpha, y, x. Okay? What this formulation gets you is you just plug in this sum of alpha, y, x into everywhere you had w previously, wx plus b, right? So you can plug that in for the normalization term. You can plug it in for the hinge loss term. And again, I'm going to skip through this because I am not going to test you on the derivation of this by any means, right? You get from this formulation, the so-called primal support vector machine version, which is what we can do with gradient descent on the weights, to a version of it which just has these alphas, x's, and y's. And now we can do gradient descent not on the weights, but on the data points. Wait, what? On the data points? What do you mean? Remember this picture? See these things? These are the 3 data points that uniquely define the solution. These are the support vectors. See, the thing about these alpha terms, these constants, is that most of them are 0. That is, most of these data points out here have 0 influence on the solution of the problem. What data points have an influence on the solution of the problem? Only the ones that are the closest together. Only the data points where the positive class and the negative class get close to each other are important in determining where the solution should be. Data points out here can change, right? Like I can take this data point right here and I can move it over to there. If I do that with logistic regression, I am going to influence where the decision boundary is somehow or other. Okay? If I do that in a support vector machine, it does not change anything. The actual answer stays identical because there's no way that's a support vector. It's too far away. So its alpha remains 0. It has no influence on the solution. Support vector machines are robust to changes in the noise structure of the training data in that way. The only data points that noise is going to change the answer on are the data points that are very close to where the decision boundary is. Does that make sense? Okay, just a little bit more about these support vectors. We had to pick them such that on one side we could form a line. This told us the slope. And the other side told us where the other hyperplane was, right? This slope, and this slope, they're all the same slope. They're determined by the direction of W. But we had to pick 2 support vectors on one side to define the slope. For a linear support vector machine, this is what, in 2 dimensions like this, you're going to have 3 support vectors. In higher dimensionality, you're going to have more support vectors, right? Because you need to define the hyperplane if this is a 3, 4, 5-dimensional set of inputs. So you need more data points to define a hyperplane. Okay? How do we find out which alphas are non-zero and are support vectors? Because that's our remaining question. Well, it's really just this simple. We do gradient descent on this. Now we're not, okay, what changes? Alpha is our parameter we're optimizing for now. It's still a minimization problem that we can solve with gradient descent, but we're now picking alpha, okay, instead of W. It's still solved by gradient descent. It's still a minimization problem. It's just been reparameterized for alphas. And the structure here is such that most of these alphas are going to be driven to 0. So, some trade-offs here, right? Originally in the weight vector is of size and number of variables. We can call that D. The primal is in D parameters. But in the dual, because originally we have to at least start by considering all the data points, it's parameterized in size of n. Okay, so it's potentially pretty big. So in cases where D is, the number of variables is way bigger than the number of data points, I mean, you're screwed because that's a hard regime to be in, but at least support vector machines, it's very efficient, right? So support vector machines in the dual formulation, they're pretty efficient up until n gets internet sized, right? Like one of the reasons why support vector machines are not cutting edge is that feeding it all 1 trillion pictures of cats on the internet is going to break down because of this, right? Your learning problem is now the size of the number of data points, and 1 trillion cats is just too big. Okay? So again, 2 forms of the classifier. The primal, where we're parameterized by W, the dual, where we're parameterized by alphas. Okay? And again, what we're looking at here is that we're looking at a linear combination of data that we have. And that data, well, we only care about the data that's close to where the decision boundary is. So in this respect, it does have a flavor of like k nearest neighbors. What's my nearest neighbors to the decision boundary, right? I just have to find where my near neighbors are and care only about them to find the solution. So there is some correspondence computationally here. And like k nearest neighbors, we're not real good in giant data problems. Okay? Okay. So, I had animated moving data points. I have to draw it. So if you're super confused by my dual formulation coverage, I refer you to the great and late great now, Patrick Winston, who can cover this stuff like nobody else on a chalkboard. So these are good YouTube lectures if you want to understand the Lagrangian multiplier method. Okay. So I don't want to cover these because we've already covered them. Okay, our last thing with a support vector machine. We need to pick that C. We need to pick that hyperparameter that makes the trade-off between the margin size and the hinge loss. So what does it look like? So C is the inverse of lambda, right? When we have a big C, we are weighting the hinge loss heavily, and we care less about margin maximization. So a large C results in a big weight vector and a small margin. Okay? When I pick a small c, that results because we're weighting the hinge loss less and the margin size more, that results in a much smaller weight vector. That much smaller weight vector means the margins are bigger, but we've allowed some stuff in the gutter, right? We allowed stuff in the gutter. That hinge loss term had much less influence. Okay, let's look at the difference between the decision boundaries. Let's ignore the margins and look at the decision boundaries. So this one was highly influenced by these 4 data points, right? And nothing else. These are, the circled things are the support vector solutions found. Okay? This one uses linear combinations of all of the data points that are in the margin or on the positive hyperplane or negative hyperplane. Okay? So all of these have an influence. Think about k nearest neighbors. What happens when k is small versus k is big? Anybody want to tell me about that? What is the shape of our decision boundary? Yeah?
When k is small, you're more easily influenced by outliers, and when k is big, it's a simpler shape because you need more instances.
Exactly. So individual data points can have huge influence, and if one of them is a noisy example, like an outlier, you can get crazy results. Okay? When you've got large number of k, you're averaging across lots of other voters, right? That's the fundamental. Big K means more voters, you're averaging. So if one of them is noisy, who cares, right? It gets voted down in the average, okay? So, same thing's happening here. This data point here has a lot of influence in determining the slope, right? So here, you can see the slope of the decision boundary is a little bit steeper than it is here. This is a shallower slope. Looks like the y-intercept's a little different too. So kind of like this is above the 2 and this is right on the 2. So it looks like small change because we averaged across things. Again, this is the more regularized solution, right? You would assume it's probably going to generalize better to noisy new data. That's the assumption with higher regularization. That's why we do it. Hard margin classifiers. So this, by the way, this is still properly fully separable, right? This data set, even though there's a lot less space in here than on the last data set we were looking at, you can still draw a perfect line in there and get 0 training error. What happens if our data set is not linearly separable? Well, hard margin solutions will never find an answer. It'll just bounce around and never finish the gradient descent on a big C value. Okay, you'll find this out. When you do scikit-learn and you up the C value, what's going to happen is the gradient descent is going to either never stop or it's going to trigger the I've hit 10,000 iterations and I'm done even though I don't have a good solution that scikit solvers usually implement. So you'll see like a little patch of warning messages saying, warning, no convergence. No convergence means I never got to a good answer. I just stopped because I hit 10,000 iterations of gradient descent, right? So hard margin can make it impossible to find a solution if the data points are non-perfectly separable. Soft margin, small c values, right? We're going to let some stuff happen in here. We'll let things into the margins. We'll let misclassifications happen and not care too much. So this will converge even in non-separable cases much more easily. Is this making sense-ish? I mean, obviously trying it will really cement it. But that's for the assignments, right? What questions do we have? Somebody must have a question. Yeah.
How do we decide without knowing beforehand which of the 2 C values would be better?
Model selection. It's a hyperparameter. Let's do some cross-validations. Let's see which one has the best validation set performance, and let's use that one. Right? Good question. So C becomes a hyperparameter, just like lambda was that one time. And again, it's the same idea. Okay, so here's your support vector machine. We're going to place a decision boundary such that some combination of factors is satisfied, that the margin is as wide as possible, and that the fewest errors are made. W can be either solved explicitly, or we can do it in the dual form, which is generally speaking computationally more efficient. Okay? So we either solve for W or we solve for alphas in the dual form for these parameters and look for the non-zero alphas The non-zero alphas are our support vectors. At decision time, it doesn't matter whether we're primal or dual. We're still just doing linear algebra, wx plus b, or alpha yx, right? So what's the difference here? I'll let you think about this. What is the difference between logistic regression and linear support vector machine? Come back and tell me on Friday, okay? Have fun, everybody. Good luck on assignments. Oh yeah, and assignment is late, right? Everybody knows that, right? We lost track of the assignment during the setup for the exam, so it was only released late on Monday. And I forget what the deadline was that we put out, but it's definitely on the weekend, right?
The deadline is Friday. Is it Friday or Saturday?
Yeah, whatever it says on Campus Wire is correct. It's also a smaller assignment. So, oh no.
Also, the lecture slides for Monday aren't up, and they're important for the assignment as well as the lecture quiz.
They're up now? Okay. Yeah, I just pushed right beforehand. I apologize. I must have added it to my local repo and then not pushed. I'm sorry. Hey.
I was wondering, like, if we have multi-class,